I'm David Weintraub. I'm a professor of astronomy at Vanderbilt University in Nashville, Tennessee. And I'm very pleased to chair this Royal Institution conversation with two tremendously accomplished astrophysicists, Dr. Carole Mundell and Dr. Hiranya Peiris. They each have contributed an autobiographical chapter to the book, The Sky is for Everyone, Women Astronomers in Their Own Words, published today in the UK and edited by myself with Virginia Trimble. The Sky is for Everyone is an internationally diverse collection of autobiographical essays by women who broke down barriers and changed the face of modern astronomy. Before 1900, a woman who wanted to study the stars had to have a father, a brother, or husband to provide entry. The considerable intellectual skills of women astronomers were still not enough to enable them to pry open the doors of opportunity for much of the 20th century. This book brings together 37 stories from many of the tough and determined women who flung those doors wide open. Taking readers from 1960 to today, Virginia and I hope this anthology will serve as an inspiration to current and future generations of women scientists while giving voice to the history of a transformative era in astronomy. Dr. Trimble and I extended invitations to 49 scientists to contribute chapters to this book. To our complete amazement, 39 of them accepted our invitation, and 37 of them completed their stories. Our instructions to our contributors were simple. Write about your life as an astrophysicist and the path you took to get there, and make a personal choice as to how much of your story will be about your life as a female scientist and how much will be about your scientific works. The book's 37 chapters are international in scope and include contributions by astronomers born in Argentina, Brazil, Canada, China, England, France, Greece, India, Israel, Japan, Lithuania, Mexico, the Netherlands, Northern Ireland, Poland, Romania, Scotland, Sri Lanka, the United States, and Zimbabwe. Now let me introduce you to my two co-conversationalists. Carole Mundell is now the Hiroko Sherwin Chair of Extragalactic Astronomy and founding head of astrophysics at the University of Bath. She studies cosmic holes and gamma ray bursts. In 2018, she was appointed as the Foreign and Commonwealth Office's first female chief scientific advisor, and in her role as Chief International Science Envoy in the Foreign, Commonwealth, and Development Office, advised on the impact science can have beyond the confines of the lab on social, economic, and political objectives. She also served on the Scientific Advisory Group for Emergencies and was involved in the UK's COVID-19 response plan. In 2016, she was named FDM Every Woman in Technology Woman of the Year and is a vocal advocate for diversity in science and for ending discrimination and sexual harassment within academia. She is a fellow of the Institute of Physics and in 2021 was elected to the presidency of the UK Science Council. Hiranya Peiris is now a professor of astrophysics at University College London, professor in cosmoparticle physics at Stockholm University, and the former director of the Oskar Klein Center for Cosmoparticle Physics in Stockholm. She now leads a large European Research Council project related to the Rubin Observatory. She combines observations, theory, and advanced statistical techniques to conduct research that sheds light on the physical origin of cosmological structure in the first moments of the universe. She was awarded the Fowler Prize by the Royal Astronomical Society in 2012, the Fred Hoyle Medal by the UK Institute of Physics in 2018, the Göran Gustafsson Prize in Physics by the Royal Swedish Academy of Sciences in 2020, and the Eddington Medal by the Royal Astronomical Society, and the Max Born Prize from the Deutsche Physikalische Gesellschaft in 2021. And she is a fellow of the American Physical Society. She shared the Gruber Cosmology Prize in 2012 and the Breakthrough Prize in Fundamental Physics in 2018 as a member of the WMAP science team, and the Gruber Cosmology Prize in 2018 as a member of the Planck collaboration. Carole, I'm going to start with a question for you. How did you end up pursuing a career in extragalactic astronomy, chasing down gamma ray bursts?
Well, David, it's lovely to join you and Hiranya this evening, and hello to our audience. So my career has been quite fortuitous and in some ways accidental. I always loved maths and equations and puzzle solving as a child. And when I went to university, I originally went to Glasgow University to study physics and maths, but I ended up on a path with astronomy included in there too. I didn't take to it immediately, but a famous supernova had exploded in 1987, and the first detection on Earth of exotic particles called neutrinos had been made. So I was very sort of enthralled by the idea of these exotic particles as tracers of extreme physics in the universe right as a teenager. And so in some ways that thread came through my career. I began my career doing my PhD at Jodrell Bank Observatory. I'd actually been offered a job in the nuclear industry, and maybe a slight overlap with Hiranya here as well. And I had to choose between a kind of a grown-up job with a really good salary and a social life, or actually continuing in education. And in fact, it was the PhD at Jodrell Bank that I found really attractive. The company kept the graduate training scheme open for me and said, yeah, go have 3 years of fun doing a PhD. So in some ways, I was in a really privileged position of being able to do the PhD and still have my options open. And I trained as a radio astronomer, actually studied gas in galaxies, atomic hydrogen, trying to understand how supermassive black holes at the heart of local galaxies were overfed to produce the kind of cosmic indigestion that we now know may be an integral part of galaxy evolution. And that was really the beginning of my career on black holes. But after a stint of a research position in the United States, I came back to the UK on a research fellowship and took that to Liverpool John Moores University, where there was a very small research group, that's sort of a burgeoning group, and they were building the world's largest fully autonomous robotic telescope, so brand new technology, which for my science at the time wasn't very useful. But the first discovery of an optical counterpart to these exotic objects called gamma ray bursts had been discovered a few years before. And these gamma ray bursts were known from the 1960s. They were detected by military satellites monitoring the Earth for violations of the nuclear test ban treaty. So very short-lived flashes of high-energy gamma rays. But the field had languished really for subsequent decades because the localization on the sky, and this is a common story in astronomy, they couldn't be localized very accurately. And it wasn't until an X-ray sort of dying ember, if you like, an afterglow of one of these had been found with a much more accurate localization that optical astronomers could then get their telescopes on and measure a distance. And they showed that these are the brightest, most energetic explosions in the universe and actually occur at the edge of the distant universe. And so the robotic telescope was then ideal for catching that fast fading light. That was really my entry into this new, exciting global field because we had that technology, but no science lead. And so I agreed to take that on and build a brand new group in order to try to understand what drove these exotic explosions and how to use them as beacons to probe the physics of the universe.
Hiranya, how did you end up pursuing a career in astrophysics, and what was your role in WMAP and Planck collaborations, which you shared those Gruber cosmology prizes?
Thanks very much to start with for inviting me to have this conversation with you and for your role in birthing this amazing book. It's very, very unique and unusual, and I've learned a lot from it too. Okay, so my life story is very meandering. So I just decided to take one thing out of there to work out when did I actually decide to become an astrophysicist and felt I was able to do it. So I was one of those kids who wanted to be an astronaut from a very young age. So I kind of had this goal in mind. But because my life took so many meandering turns after that, I think the point at which I really started pursuing this career path seriously was in the second year of my undergraduate degree. So I happened to obtain what's called the Summer Undergraduate Research Fellowship at the California Institute of Technology. And that gave me a chance to work on the data from the Galileo probe to Jupiter. And that was at the Jet Propulsion Laboratory in California. It's really, really exciting. It was magical. I enjoyed it so much. And I thought that the scientists I worked with had the best job in the world. And also importantly, the job paid me, which meant I could afford to apply to PhD places in the US, where I decided I wanted to go. So having that experience that I could do science and was good at it, and also that feeling of belonging that I had at JPL as being part of a scientific community and being included in that was very, very important in my subsequent career choices. So to come to WMAP and Planck, so I worked on WMAP as a PhD student at Princeton. and on Planck as a junior faculty member. So these were the second and third satellite missions that were designed to study the so-called cosmic microwave background. This is the ancient light that's left over from the Big Bang. And it was released when the universe was very young, only about 380,000 years old. And ever since then, it's been traveling through space, through the universe as it expanded and cooled. And we see it now 13.8 billion years later. And we can observe this very, very weak radiation by putting extremely sensitive detectors out in space and also on very like high and cold and dry places on the Earth. And with these observations, we can do a kind of time travel because light has a speed limit. When you look out into the distant universe, you see things as they were in the past. And by studying this ancient light, we can figure out the basic properties of the universe, its constituents, its geometry, its age, and even some aspects of the physics of the Big Bang. So my role in these teams was to build analysis pipelines to connect the theory with the data. So making theoretical predictions for what we should see in the data and comparing that with the data, and doing that for many different cosmological models so that we can work out which models don't fit the data and which do. So that allowed us to work out which model best matches all of the data. And in my work, I particularly focus on trying to understand the physics of the very early universe, the very origin of all of the structure we see in the universe today. And overall, I guess I contributed to the work of these teams, which helped define what we now call the standard model of cosmology.
I want to go back a moment to something in your story, Hiranya, and I think both of you have had these experiences, but when you were an undergraduate and you worked at Jet Propulsion Lab, you describe having this aha moment when you discovered something that nobody else knew. Mm-hmm. That to me is the incredible excitement of science. Can you describe what that felt to you, what it still feels to you when that happened?
So I remember having a moment like that. So the Galileo probe sent back data in like lines one by one. They would appear on one of those old style monitors. And there was a picture of the surface of Europa. And I was a pretty geeky kid and I was really into science fiction. And I had all these ideas of what Europa would look like. And then I saw it. And I think that particular picture, I might have been the first person to ever see that. And that was just, I can't describe that experience. And it's something that, you know, subsequently I've experienced many times. Incredibly lucky as a human being to see that. And yes, it is fantastic.
Can you echo that, Carole?
I can, absolutely. I mean, I think that there is this myth that, you know, the arts and the humanities are creative and science is in some ways dry and boring and rigorous. Of course, we have rigor, we have the scientific method. But for me, it's a fundamentally creative process when you're working at the frontiers of knowledge. And it might be that you have to invent the technology in order to answer a science question, or it may be that you're taking the data from that new technology and you've predicted what it might see, then you discover something you weren't expecting, or you might actually test a theory. And when you have that moment, for me, it's a very personal feeling. It's often a very private feeling. So we work in teams, but it's a very private moment. It's like a spark. Mm-hmm. And you almost don't believe it. There's just a rush of excitement and you think, wow, and you take a breath. And then very quickly after that, the scientist in you starts to kick in and you say, well, wait a minute, let's check. Before I tell anybody, I'm going to have to check. Then you get the doubt and a little bit of the humility that in principle makes you a good scientist. And then you start to worry, really need to check this properly. And then I think the next step for me is, you know, to speak to a trusted collaborator and say, over here, could you come and do a sanity check? Because I think I've found something, or I think this is it. Do you think I'm right? And then I think that's the moment when you get the next spark, you spread that spark around, the next person says, well, check it in a different way. Then the excitement starts to grow. Then you craft your publication. And that's when you're ready to start to think about how you communicate that to your wider scientific community, and then use all the processes that we have, like journal publications and conference talks, and ultimately press releases to then, or, you know, public talks to then communicate that to the wider public. And it's a very, very special feeling. And like Hiranya, I've had it a few times in my career. And it's the moment that you hope and you wait for that reminds you, this is why I'm a scientist. This is why we do, if you like, all the hard slog and all of the other stuff that goes with it, and moments of failure as well. You know, there's lots of failure within science. And so it's that spark that balances out the moments of disappointment where you have to pick yourself up again and start from scratch in some ways.
And I think those moments are so amazing, so special. I wish all of our listeners could have those experiences. They're truly amazing. For either one of you, we'll go back and forth, but through your careers, especially early in your careers, you must have had some mentors or some colleagues or some role models who enabled you to keep moving forward in your careers. Do you want to say anything about how that might have happened for each of you?
Yeah, I'm happy to take that one, David. I think I was reflecting on this really, and I think there are different kinds of role models in my life. So there were the very early family role models. So the family support that I had from my mum and dad, who we were not a university educated family. There wasn't that in my past. And so there was that sense that they encouraged my curiosity and they encouraged me to follow what I was interested in and supported me in that. My dad was a biomedical scientist who worked in the National Health Service. So worked long, hard hours as a public servant, but had that spark and that interest in the world. And I guess I caught that from him early on. But then I think through my career, there were people who were instrumental in helping me keep my career aspirations on track. So for example, Dr. Jim Cohen at Jodrell Bank Observatory. When I first applied there, I actually applied to do a master's project because I wasn't sure what I wanted to do after my degree. And he was the one who actually encouraged me to do a PhD. And when I didn't actually respond, I went away for a few weeks to think about it. And actually, again, there's a confidence question in there too. I had the job offer. They were at different grade disparities, a second class degree to go for the job, an upper second or above to do the PhD. And I was lacking confidence in my final year at university. And he called me up and he said, "You haven't responded to our offer. What are you thinking?" And we had a conversation and he said, "Well, if you get the grade that you need for PhD and you want to do a PhD, come to Jodrell Bank and do it. If you don't, you come and you start on a master's and we'll convert you to a PhD. So make it a life choice. Don't make it a degree choice." And the fact that he had the wisdom to call me, he knew that it might be a confidence issue, but he saw something in me and gave me that really open choice. So I think there are those sort of hidden guardian angels that help to guide your path. And they're very quiet in the background, but they have a really seminal influence, I think, on your life. And then there are women in the book, like Professor Dame Jocelyn Bell Burnell. You see her name come up many times across the generations, both practical mentorship, but also being an icon in the field and actually seeing something. You can't be what you can't see. And I describe in the chapter how when I was an undergraduate at the University of Glasgow, I remember only one young woman lecturer out of 4 years. And so there was no sense that this was a path for a woman until, Jocelyn came and gave a talk to the Student Society. And I thought, wow, you get women astrophysicists. This is an option. And I think she influences a number of women in the book. And there are other women, of course, who wrote their PhDs up before me, whose research papers I was reading as a PhD student and who were kind of idols for me in my field. And it's lovely now to be connected through the book, because as a student, I never had the courage to write to them or reach out to them. I just read their work and it influenced the research that I did.
Right.
Yeah, so I completely related to this last point. I mean, to me, it's like an incredible honor to be in a book with all these very inspiring people that I'm lucky to have met some of them, but many of them are just kind of up on a pedestal, and it's just really inspiring to read their stories. I feel like I was really lucky in my early life. My family supported my interest in science from a very young age, and I was lucky to have many female role models, including my mother. She was one of Sri Lanka's first civil engineers. I had aunts who were doctors and teachers. Sri Lanka had the world's first woman prime minister. To me, it wasn't even a question that being a woman would prevent you from doing anything you wanted. So that wasn't even an idea in my head. And so later in life, again, relating to something Carole brought up, there were many people dotted around where I'm not going to mention names because I would I would leave somebody out that, and that would be mortifying. But, sometimes mentoring has just been one short conversation, somebody giving you time, when you're young and you're not sure of things. And that comes at a critical time in your life. And they might not even remember they had this conversation. But to me, it was just, life-changing, right? And one constant influence from my early career till even now as a senior faculty member has been my PhD advisor. I haven't directly worked with him since those early days, and he's one of the busiest people in our field, but he always has found time whenever I wanted to talk through something, anytime in my career. And that commitment to young people and mentoring is something I really valued. And that mentoring style, and also the breadth of his interests and his leadership style, where leadership is not about like putting yourself up above other people, but about, it's framed as a service to your community. All of those things that he, profiled through his career has influenced my own career choices. And I also feel like, I can learn from anyone, both senior and junior people inspire me. And sometimes the scientific rapport with a colleague has just kind of opened up new research directions for me. And then I, end up prioritizing those because it's just so fun to work with that person. And, I talk about a few of those in my chapter. But I've always enjoyed working with students, and their excitement and enthusiasm really inspires me. Sometimes you think, mentors are older people, more advanced. But to me, I've learned a lot from young people. And I think especially on issues of equity and inclusion in our field, the young people are the ones leading the change. And I feel that is extremely inspiring to me. And I feel like I have to step up.
Yeah, I agree with Hiranya on that last point. I think the energy and the fire that come from the younger people knocking at the door, in some ways holding us to account as we're more senior. And I think, but also reminding us to be courageous, because sometimes I think when you are, as senior women, we are still isolated in our field, and it's lovely to connect across this book. But, we have either been trailblazers or we've been the only woman in the room. And I think you do suddenly realize you've lost the energy or the courage to say this isn't right, or the sanity check. And it's that younger generation that say, actually, you're there, you do something because we see it and we want it to change, but you've got the position in principle and the power to do something. So it helps you to keep raising your voice in those difficult situations.
Yeah, I completely agree. I mean, I frequently find myself in rooms where I'm the only in many different dimensions. And, it takes guts to open your mouth and contradict a whole room of people that don't look like me and don't have my experiences. And, the young people's fire and energy and courage actually inspires me to just, I have to now step up. And I think that's a really important change possibly in our field now, that there are all those people who don't want to make do or work around. They want to dismantle the barriers. And I think that's a sea change that astronomy, I think, has led, and now also going into physics as well.
I think one thing that hasn't changed across the generations, and I see that looking through the 37 stories, is that the young people need senior mentors like the two of you to help them break down their barriers, because they don't have the power to do it. But us old people, we need those young people who have the fire in their bellies, who want to make change happen. So it takes both parts of it. Something I was struck by what you said, Carole, you had only one female instructor as an undergraduate at Glasgow.
Yeah.
What would students see today at your institution?
Oh, unfortunately, not the dramatic change that I would like to have seen over the years. I can't speak for Glasgow. I can speak for Bath. Bath's not as old as Glasgow. I think Glasgow was founded in 1471. I may be out by a few years. Bath is a modern university, so it's just over 50 years old, and it was set up as a science and engineering college and then university. So it has that legacy. of that white male-dominated aura around it. We have our humanities and social sciences as well, and they're a bit more diverse. So it is a battle, and it's a small university as well, so that it also suffers, I think, from scale. The bigger the organization, maybe the quicker you can try to drive that change, or you can start to spread pockets of change. And so I think for me, it's a little better. My group now, I think, is sort of 50-50. And the last time I counted, we were represented across 12 different countries, including our 12 PhD students. But physics is still quite stubborn. If you look at the UK statistics that the Institute of Physics published recently, for the last 20 years, we've been stuck on about 20% women taking physics-related degrees in our universities. Some universities do a little bit better. And then, of course, that's the beginning of the pipeline, and then the attrition is quite steep after that. So when I was head of the Department of Physics, and I chaired the National Institute of Physics Forum for heads of physics departments, there were only 2 women who were heads of physics in the whole of the UK. And then, of course, you do that for a number of years and you cycle off again. So it's still a persistent problem, I think. And we still need to do something radical, because otherwise we can't really justify going into schools and saying to girls, oh, you must study physics and astrophysics, if we don't make the profession welcoming for them, and a place where they can thrive once we've triggered their interest and brought them in. To then slam the door in their face of aspiration, I think is criminal, and we have to do better.
I was just trying to reflect, was there a single female instructor, either during my undergraduate degree or my PhD? And I do not believe there was a single one. And I think that this problem indeed is much better in astronomy than in physics. So the Royal Astronomical Society did a survey of the field in the UK a few years ago. There were, I think, 30% junior faculty and 20% mid-career, 10% senior women in astronomy. I think if you look at the numbers of physics, it'll be astonishingly poor, with very little change. My department at UCL in the astrophysics group has got quite a few female professors and junior faculty. I think they've done well there, but it is not reflected across the physics department.
So change is happening, but more change still needs to happen. Mm-hmm. For both of you, you've had experiences at conferences, at your universities, at meetings, where you were stereotyped in negative ways because of your gender or ethnicity. How easy or challenging was it for you to enter this field and become successful because of problems like that? And has this changed much?
Hiranya,
I'll try to take that. I mean, as I said, I had these very, very good initial conditions. I didn't have this idea in my head that anybody should be able to tell me I can't do something because of my gender and ethnicity. And so, I feel like that is a form of brainwashing. And we didn't have that in Sri Lanka. So when I moved to the UK, I mean, I think, that's when I started to experience these kinds of views. And I think by the time people acted towards me in ways to try to damage my resolve and self-confidence, it did happen, but it was too late by then to try to brainwash me that gender or ethnicity had any bearing in my ability to do science. Of course, there were upsetting incidents, but I think I barely noticed them. And I mean, I don't think if I didn't have a very thick skin and I wasn't very stubborn, I wouldn't be here, right? So it's a selection effect, right? I am here partly because I had personality characteristics that don't really care that much about what other people think. And I have a very clear idea of what I want. And so I'll find a way to achieve it. But that's not the case in general. Scientific ability does not have to be correlated with those personality characteristics. So I think we are driving, even now, quite a lot of people out of the field because of toxic workplaces and toxic attitudes at conferences. And it can get much, much worse than that as well. And I think that the overt type of this kind of attitude is much less probably than what some of the earlier chapters in the book recounts. but I think the underground level of it is still there. And you just have to have a few of these experiences to demoralize someone at a vulnerable time in their career. And then they get kind of, pushed out, and you don't hear their voices. And so this is definitely still an issue in the field, and it is a systemic issue. It replicates itself even if the individual bad actors can be taken out. So it's a systemic issue, and I think it has to be changed at a level of the system, of the community.
Carole, you're doing a lot of work in that regard, aren't you?
Yeah, I agree with Hiranya, really. I think there are structural barriers that actually have become more apparent to me as I've become more senior. And so like Hiranya, I had, periods in my career, like when I was doing my PhD, where it felt a very welcoming and inclusive place, although very male dominated. I wasn't aware of being a woman. I was a scientist. The University of Maryland, where I was a postdoc, it was the same. It was an exciting, creative environment. You talked about ideas and you moved your science agenda forward. And so that, for me, thinking about ideas was, and not meeting those challenges or not being aware of them was important, because when you are battling against those challenges, whether that's a toxic workplace culture or the kind of environment that enables sexual harassment to happen, or whether you're hitting structural barriers or sometimes that benign sexism where it's not expected that women can succeed, we sort of see those things as much more subtle and covert. It's tiring. And I think when you think of the environments in which we've worked, where we felt we were free to be scientists, there's so much energy that you can put into your science. And then when you hit these barriers, they're not inherently because of your ability to do science. They're actually external and they're imposed. They start to drain your energy away because you're being distracted from the science. So whether that's for yourself, whether you're supporting other women or other minorities, because they're actually suffering in that environment too, which is something that more senior women start to do as they have the power and the influence to do that. That starts to drain you away from the science. And that actually degrades the whole of the quality of the science that we do. You have a monoculture. You're only going to get one answer if everybody, whatever their characteristic, thinks in the same way. So it damages the quality of the science. So for me, I think the work that the learned societies are doing, and now in my role as president of the Science Council, we have a very clear set of accreditation for qualifications in different science areas. So we work in academia, we work in the public sector, and we also work in the private sector. And I see in industry and in the public sector, very different career paths and very different approaches to driving those inclusive behaviors and removing those barriers that hasn't yet reached academia, I think, academia systemically. So I think Hiranya is right that we have to look at systems. We have now things like Athena Swan, which is a UK system for looking at universities and actually asking them to do some self-assessment. And I think that was very important when the senior women who set that up some years ago, they were actually saying to universities, sort yourselves out, or you don't get funded. And that was quite a step change. The data are important. You need to look at the data, but then you have to be honest about the causes and the biases within those data. And I think, as Hiranya said, astrophysics in some way has been ahead of the game by raising some of these behaviors. We've had some very high profile international cases of scientists exposed for sexual harassment, and we've had those conversations. I've been asked, is astrophysics worse than other fields? And I say, no, we're having the difficult conversations. And then behind the scenes, we're trying to tackle these because we collaborate internationally. We have big international collaborations. There's millions of dollars being, funded into satellites or telescopes or the technologies that we drive, and generations of scientists who want to come along and use those facilities or develop them. So we have a huge privilege to do that science. And we are now developing those instruments and actually the courage to call those behaviors out, but also to help the senior managers around us to understand that the sort of permissive behaviors in the past, well, it's just the way he is, or it's just the way our lab is actually not acceptable, because it excludes and drives people out of the field who would have contributed to scientific knowledge and pushing the frontiers. And we've lost those from the field. They may be happy doing what they're doing elsewhere. It's a loss to science and to our organizations.
Yeah, I'd like to pick out a couple of points there. So it's clear reading the earlier chapters in the book that to get a faculty job in those days, basically your advisor called somebody up, and it was usually an all boys network. And then there was no process, there were no open adverts, nothing. And it was just about who you knew, and then those people got jobs. So Athena Swan that Carole has mentioned, I mean, of course, it's not the last word and it's a long way to go, but in the UK, I think Athena Swan had a very pivotal role in laying out that all jobs had to be advertised openly, had to have procedures around those, promotion criteria were published openly, and everybody was looked at for promotion. And I think that has had a transformative effect in actually quite a short time. So that is a systemic approach to the problem, and I think it has had a good outcome. So I was pleased to read that the NSF in the US actually requires reporting of PIs who have been found guilty of sexual harassment in an institutional process, and they can't get that funding. We don't have that yet in the UK. I think this is something that we need to advocate for and get. And some private foundations in the UK have that now. But the government funding is still going, I'm sure, to people who have these kinds of issues in their histories.
Yeah. And I think organizationally it is, again, that accountability. You know, there's always a way to move around a formal system, but actually enabling organizations to understand that they're both responsible, they're publicly funded organizations, they are responsible for the workplace culture. And ultimately within the UK, you know, we have the Equality Act 2010, and you're in violation of these government acts and the laws, really. We have the Nolan Principles, the 7 Principles of Public Life. Our universities are publicly funded institutions, and everybody working in them are actually required, whether they know or not, to adhere to those Nolan Principles. So we have the frameworks, and it's about driving through the processes and making sure those processes are used correctly to make sure that we fix these systemic problems.
Yeah, if I may, I'd like to make one personal point. There's a chapter in this book by a professor who was a very senior professor when I was a PhD student. And as a PhD student in that department, I encountered an extremely inclusive and fantastic environment. And it was shocking, and I mean, it caused me a lot of anger to read about her experience in that environment, which was not inclusive. And the comments that were made about her and why she got her job and so on. So that was going on at the same time in the same department. Yeah. And I don't know, I feel very angry about this.
And Hiranya, I think that's a really interesting point. Sorry, David, you're going to get a word in here. The vertical communication, I think, is also really important, because as we become more senior, we become busier, we maybe get isolated. But actually, the junior scientists also don't necessarily know what the senior women are experiencing. We don't necessarily want to come out and say, I'm having this terrible time as a senior leader, because you feel it's your responsibility to fix what's around you. But I think a little bit more of that sharing. And as you say, it's almost reverse mentoring again around the culture. So yeah, it's an eye-opener for me. I think I know the chapters that you referred to.
I'd like to ask you to switch gears a little bit and talk a little bit about astrophysics, the astrophysics you've done, the astrophysics that excites you. Hiranya, you, for a little while, for several years, you were the director of the Oskar Klein Center in Stockholm. Can you tell us a bit about it and what you tried to achieve as director of that institute?
Of course, yeah. So the Oskar Klein Center is really an experiment in the co-location of scientists as a way of stimulating interdisciplinary collaboration, but doing it in a bottom-up way rather than imposed top-down way. So it's an umbrella organization that includes about 150 scientists, and they belong to 3 different departments in 2 universities, Stockholm University and the Royal Institute of Technology. So we have scientists that work on cosmology, astroparticle physics, high energy physics, astrophysics, astronomy, as well as builders of instrumentation. And they're all co-located in this beautiful building called Alba Nova in Stockholm. So my job as director involved essentially stimulating cross-pollination between these very diverse groups and identifying and building critical mass among the most promising cross-cutting directions, and eventually quite a lot of work raising funds through competitive schemes to give these directions, large projects, their own legs so that they're self-sustaining. I think I can identify 4 significant accomplishment that I'm really proud of. I negotiated to get us to join the Vera C. Rubin Observatory project. Vera Rubin, of course, is, you know, her inspiration and her work for the field looms large over this whole book. So Rubin Observatory is named after her. So we joined that project with a large group of faculty, postdocs, and students. And these people are working on many aspects of preparing for the Rubin data. I also set up quite a thriving research environment, investigating a compelling dark matter candidate called the Axion, both in the lab and with astronomical data. This has now led to a very exciting international collaboration to build a new type of direct detection experiment called a plasma haloscope. The idea for that came through two postdocs setting up a journal club, which started a whole bunch of conversations between people working in different fields. And so that's an example of how cross-pollination can happen in a bottom-up way. I also built up a large and quite active group working on multi-messenger astrophysics and cosmology. And so the multi-messengers here are electromagnetic radiation, gravitational waves, and neutrinos. And these provide different views on interesting extreme astrophysical phenomena and also on cosmology. And I also spend quite a lot of effort renewing and building up connections between the Oskar Klein Center and Nordita, which is the Nordic Theory Institute.
Carole, do you want to talk about some of the things you're looking forward to doing, the big science that's ahead for you?
Yeah, thanks, David. So I think black holes really knit all of my research together. And I think it's quite incredible to think that as a species, we can conceptualize the universe, we can discover the mathematics and write down the mathematics that really codes the universe and gives us testable predictions. And for me, it was really Einstein's general theory of relativity, which he published in 1915 after being helped by the eminent mathematician Emmy Noether. She worked at the University of Göttingen. And his general theory of relativity made three very important predictions. Other scientists analyzed those equations. There were only ever, I think, three analytical solutions, exact analytical solutions discovered. One predicted the expansion of the universe, and that was very, seminal to Hiranya's research, and obviously proven experimentally in the 1960s with the detection of the cosmic microwave background. The second predicted that black holes could exist in nature in theory. And we now pretty much are relaxed about the idea of finding black holes at centers of galaxies and exploding stars. And the third one was the prediction of gravitational waves or ripples in space-time when massive objects collide. So my research kind of pulls all of that together, and the research groups that I built and founded have gradually grown in terms of the scope that we bring into there. So when I was a young researcher, I studied a class of local galaxies called Cepheid galaxies, which did have supermassive black holes, which were active. They were feeding on the material in the host galaxy. But I was a bit odd because in those days, we kind of hadn't put these together. We knew about big, powerful quasars that were found in more distant galaxies, big supermassive black holes that were triggered into activity. But the local galaxies had been less well studied, and they were not in big train wreck systems. So the idea is that the quasars were galaxy collisions early in the universe, in the violent universe, but in the local universe, the galaxies were much more well established. So I would go to conferences where people were studying the host galaxies, and I would talk about the fuel in the host galaxy. This can potentially fuel the black hole. And they'd be saying, no, we take all the active galaxies out of our samples. Then I would go to conferences on active galaxies where people were studying the very high energy radiation coming from very close to the black hole, and they thought I was crazy that I was studying the host galaxy environment. But now it's great to see that these fields have now merged with the discovery in the late 1990s that probably all galaxies host supermassive black holes, and they probably all go through a period of activity through in their lifetime. I mean, think of it a bit like feeding children. If you overfeed them, they get indigestion, they make a mess, and then you have to starve them for a little while. And that sounds like child cruelty, but you reduce the food that you give them until they're healthy again. And this is the evolution of galaxies. And then, of course, when I moved into the time domain side, I'd already done that a little bit in the radio, but opening up this sort of same physics, but at much shorter timescales. So for the supermassive black holes, we have to do large statistical samples. And again, as Hiranya mentioned, the Rubin Observatory will be seminal in this. because they take millions of years to evolve. So we look at many of them to get snapshots. But of course, when you go to smaller black holes that are produced when massive stars, 200 to 300 times the mass of our own sun, reach the end of their life and collapse to form black holes and then produce these gamma ray bursts, those evolve very quickly. So the gamma ray flash is gone in seconds. The optical light might be gone in minutes or hours. And so really what we opened up with our robotic telescopes when we built the group in Liverpool was actually, we had a suite of telescopes around the world. We built 3 2-meter telescopes. We had one in the Canary Islands, one in Hawaii, one in Australia. So 24/7 sky coverage. And these are big telescopes and you're doing transient science. These are sort of the big eyes on the sky. And what we really did was we started to probe into the very faint optical counterparts, and we could really start to look at these explosions through cosmic time. And the one thing that I really wanted, apart from the fact it was very exciting at the time, my first child had been born, so he was sleeping happily through the night, and I was waking up in the middle of the night, catching the birth cries of new black holes, and building my team and negotiating, paper leadership with collaborators or competitors sometimes around the world in the middle of the night. And we were developing our technology as well at the same time. What we really wanted to answer was what powered these things. And I think for me, what was so exciting was that there were 2 competing theories. One, that magnetic fields drove these explosions, and the second was that the magnetic fields were not there. So we built a very special instrument called a polarimeter to measure a special property of the light, not just its brightness and how it faded with time, but almost what the glare of the light is. And that's the only way in the universe that you can probe directly the magnetic fields in the plasmas or soups of charged particles that produce the radiation that we detect with our telescopes. And so we made some very groundbreaking measurements very soon after the formation of these black holes and proved that, in fact, large-scale ordered magnetic fields are there. And they are responsible for focusing the material that is blasted out as the black hole collapses and the star blasts off its outer regions. And then these beams of plasmas point towards the Earth, and we see a gamma ray burst. And that, for me, was really the entry into this brand new multi-messenger universe. We're now obviously trying to develop this technology so that we can do that for gravitational wave sources. And actually, we think that 50% of the heavy metals in the universe, maybe platinum and gold, are actually formed in these dense objects. Neutron stars merge together to form black holes, and we catch them in that moment. So we're always trying to push sooner and sooner. I think my record is something like 70 seconds after the formation of a black hole. So we're always pushing the technology limits so that we can study the physics earlier and earlier. And ultimately, we really want to combine the physics that we understand on the smallest scales governed by quantum mechanics and particle physics with the physics that we understand, we think, on the largest scales that are governed by the forces of gravity. There is not yet a combined theory of gravity and quantum mechanics. And there are many bits of theories that ultimately I'm waiting for my theory colleagues to produce a nice testable prediction, and then I'll go and design the experiment to rule it in or out.
I just want to climb inside your brains and watch how all this thinking happens, because it's so exciting. Hiranya, you mentioned that you have a big new project that you're leading with the Rubin Observatory, a European collaboration. Can you tell us about that?
Yeah, let me explain what Rubin is, first of all, in case people on the audience don't know. So it's one of the big flagship projects of astronomy in the next decade. It's expected to start operations in, I guess, next year. It involves more than 1,000 people in over 20 countries. It's a huge, decade-long survey of the entire southern sky in 6 colors. And it's observing the sky in a completely new way that's never been done at this scale before. So it'll take pictures of each small patch of the sky every 3 days or so, and do that for a decade. So by stitching together those images, we can make our first movie of the universe. So this will be a new view of the dynamic universe, and you can use it in many different ways. You can shed light on dark matter and dark energy. You can get new understanding of our own galaxy and even our own solar system. And you can map out these violent stellar explosions of dying stars, and also see these optical counterparts of gravitational wave merger events that Carole just mentioned. So this project will produce like a deluge of data every night. A human being can't go through all that data and find out the subset of it that is of interest to their own science. So we have to have very powerful methods to sift through that data and present the human with a subset of it that's of interest to them. And this requires new analysis methods to make sense of it all. And just astronomers can't do it. So, we have to work with computer scientists, we have to work with data scientists, we have to use machine learning. And so all of these other fields have to interface with astronomers and cosmologists in order to make sense of this incredible and extremely complex, large and high velocity data set. So it's like an ultimate big data project. So my research on this is going to focus on, first of all, developing those very powerful techniques to make sense of the data and then use it to shed light on the physical nature of dark matter and dark energy. And I also want to hunt for gravitational wave counterparts for use in cosmological studies. But I'm mostly excited about the surprises, the unforeseen discoveries that nobody expected. So whenever we have observed the universe in a new way, we've made discoveries of unexpected things. And this is bound to happen with Rubin. I hope to contribute to those discoveries. And you can't just wait and wait for the data to overwhelm you. You have to develop methods to work out what is genuinely interesting and what is an artifact in the data. So that is also something I'm working on.
And David, if I may interject, I'm really excited about Hiranya's technology development, because I typically wake up, if I follow every satellite trigger that I get for new transients, 200 to 300 times a year. We will be getting 1 million new transients discovered per night with Rubin, and I really don't want to wake up 1 million times per night to try to figure out whether to follow them up with my robotic telescopes.
One of the fascinating things both of you have been describing is that when I started in astronomy 40 years ago, our general idea was that the sky doesn't change. You look up today, and what you see today is what our grandchildren will see. And what you're both telling us about is that the future of astronomy research, the big future of astronomy research now, is what's been called time domain astronomy, in which we're looking for the very, very rapid changes, not just changes on a human time scale, but on a daily or even hourly time scale that we may be seeing. We have no idea what we're about to discover. It's a very exciting time.
Yes. And also, I think, across the electromagnetic spectrum. So you're right, the reason we have this idea of this slowly varying sky, I mean, ancient astronomers studied how the planets moved across the night sky over the course of a month, and that was how we then discovered that, the laws of gravitation that Newton ultimately encoded in his maths. So I think we've understood that the sky changes, we understand that the sun rises and sets, and we understand seasons, but as you say, it's dominated by visible light, and that's the view our eyes see when we look up. But now the fact that we have telescopes and instruments both on the ground and in space that can catch radiation from across the electromagnetic spectrum and beyond, as Hiranya said, into the dark sector, exotic particles and gravitational waves, we then realize that we're in an incredibly dynamic universe, and that the more we open up those new windows, as we will find those surprises as well as test the laws that we think we currently have.
We have a few more minutes before we look at the questions and comments from our audience. Carole, I had a question for you that's a little sideways from the astrophysics, and that is that you spent a significant amount of time over the last several years as the chief scientific advisor in the Foreign and Commonwealth Office, and much of your effort was dedicated to international science diplomacy. Could you say something perhaps about that, but also more importantly, how did your training in science and in astrophysics help you in that role? Because you weren't trained to do that.
No, let me answer that question in reverse, David. So I think the scientific method is really important, and it's not something that's just valuable for scientists. So I think one of the most important things I did as chief scientific advisor was ask my colleagues to think about what underlying assumptions they were using when they were developing policy. Beyond that, what I used really was, I think, two things: my credibility as a research active, internationally leading scientist with international collaborators around the world. There was a credibility when I then went to work beyond astrophysics or physics or space science, whether that was in oceans or climate or biomedical sciences or global health. So when I was building up those relationships on behalf of the UK, our universities and our industry sectors, and also UK government, I was drawing on that credibility of me as a scientist, but also me as a senior civil servant. And I think what I saw was incredibly inspiring, that first of all, from the science advice perspective, the UK system is highly respected internationally, and countries really wanted to understand the science advice mechanism we had across the whole of Whitehall. How did we advise our ministers? How did we build that advice? And how did we make sure that policy was evidence-based? And then secondly, on top of that, the respect for the UK science system and the incredible international ecosystem that we have in research, people who have come to the UK to study and gone back or gone to other countries, all the collaborations that we have internationally. And I think for me, you know, we face these huge global challenges like climate change. You know, we're living through a pandemic now, possibly a second one as well. And I think, you know, those frontiers of science, as we look at the interface between humans and our environments just on the terrestrial planet, never mind when we think about whether we're being good custodians of outer space, whether the concept of space war, which is unimaginably horrific, could happen. We've seen the war in Ukraine. We've seen, you know, the sort of the reactions and the aggression from Russia, and we see the impacts on things like the cost of living. So all of these things are connected. And what was very clear to me is we live at a very special time in terms of communication around the world, but we have a set of globally connected fragile systems embedded in a natural world that is under incredible strain. And so I think that the best of science is that we can provide those solutions, but science is embedded within society, and we can't just do science in the lab. It's a huge privilege to be a scientist, but actually that needs to be embedded in society, and it needs to be for the wider good.
I'm not sure what to follow that up with. Do either of you have any additional things you want to offer before we take a look at some of the questions?
I think I just wanted to echo what Hiranya said at the beginning, which is gratitude to you and Virginia. I think the book is an incredible project. It's a real gem. I'm reading it, I'm rereading it, I'm going back and finding more connections. But I think what you also did for me, I know myself and many of us in the book, we found it very difficult to write our chapters. And I think for me, what you did with great tact and kindness was you made the invisible visible, and you helped us to look at ourselves and appreciate the journeys that we've had. And I think that that's only a good thing. And I hope that we will then go and share that with others, and that your audience will buy the book, read it, enjoy it, have conversations with their daughters, their sons, their friends, their neighbors, and actually think about you know, being good custodians of our environment, because the sky is for everyone, and we are on this really rather special planet, and we're only sentient beings for a tiny fraction of the 13.9 billion years of the age of the universe. So I think we should use that time well.
And say it better.
It was a privilege and an honor to get to work with all of you and learn your stories. And I think someone reading the book can start to look for common themes, commonalities through the 37 chapters: the importance of mentors, the importance of advising, the importance of parents in encouraging us, the importance of having books in your lives, in your environment, lots of things like that.